Hello, everyone. Let's start today's discussion. I hope you all had a great day so far. This week, we are gonna talk about two of the most useful and popular components, and more specifically, semiconductor component that we are gonna use uh, in electrical engineering when you want to uh, build like an amplifier or a logic circuit or these type of kind of like a signal processing design or the signal processing technology. They are normally use one of these two components. Now, these two components are in the category of the transistors. Okay, we are going to talk about two specific categories. One is the FET, which is field effective transistor. And in our lab assignment, we are gonna focus on MOSFETs, and the other one is BJT or bipolar junction transistor. Okay, now MOSFET and BJT. These are the one that we are gonna talk about. Now, let's start with the MOSFET and basically the field effect transistor. Now, when we talk about the MOSFET, we are talking about a semiconductor device that includes three components of the semiconductor. Either there is two N and one P in the middle, or two P and one N in the middle. The middle part, the semiconductor in the middle, we call it the channel. Okay, so if we have a P type, like the one colored in red, the P type, in between the two N type semiconductor, we are going to have a P channel MOSFET. Okay, as you can kind of like imagine, the other type, which has an N type semiconductor in between the two P type, is going to be N channel MOSFET. Now, MOSFETs and most generally the transistor all are three-gated kind of like component. MOSFET is also has three pins or three gates in that component. One called the one of the pins are called source. The other one is drain, and the third one is the gate. Okay, source and drain are basically the gates that your main signal, you want to call it power signal, would transfer through. Okay, so for example, if you wanted to like use the MOSFET, you're gonna see that as a switch. Okay, you wanted to like ignite the switch on and off, but the main current or main signal that you want to process it by turning it on and off is going to go through drain to source or vice versa, source to drain. Okay, the third one, which is the middle pin in the graph, is gate, which is the control. So the other two are the signal or like the power pins. Okay, the middle one is the control pin. Using the middle pin, you controlling the behavior of your transistor. Okay, now if you have an N-type MOSFET, the current between the two power pins, okay, the current will go from the source toward the drain. Okay, so if we have an N channel, current goes, and you can see that in the schematic, this is the symbol for the MOSFET. You can see that the current goes from the source to the drain. Now, if you have a P channel, meaning the component between the other two is P type, and the component connected to the drain and source pin are N type. Okay, if you have a P channel transistor, P channel MOSFET, the current goes from drain to source. Now, I want you to think about why N channel and P channel has different direction of the current. And I'm going to give you a hint and I want you to think about. We already covered in previous week the behavior of the diodes when two semiconductors were connected to each other. And we had the concept of the forward bias and reverse. Now, in transistor, in this MOSFET, you can see three semiconductor, but you can imagine that individually each pair would behave like a diode. You have NP at one side here, you have an NP connection, and here also you have a PN connection. Okay, so this connection here would behave the same as you saw in previous week when you talked about and you experimented diode. So now I give you the hint about thinking from the diode kind of like perspective and try to understand why in P channel we have a certain direction of the current, and in N channel the direction of the current is reversed. Are you good? Any questions so far? No? Okay. Similar to all the components that we want to analyze or want to use, the IV characteristics is the curve or the characteristics that models the behavior of our component, and we can use that model to basically analyze that component in different type of condition or when the different type of signal is applied. Okay, so if you know what's the dynamic between the current and voltage is for any type of component, okay, then you can basically analyze the behavior of that component regardless of whatever input you have. Are you good? It was like a black box kind of situation. You know what is the, you consider the black box, you know how the current and voltage behave, and kind of like change based on the change in the either one of them. Okay, so then you have the model, the mathematical model for analyzing that part of your signal. Okay, now same concept goes for the MOSFET. We said that the drain and source are the main port, or the ports that the signal that we want to process, the main one. Okay, we can call it power signal, but it's a little bit. I'm hesitating that because sometimes it's create confusion. But the main signal will be conducted between the drain and source based on the type of MOSFET that you have. Okay, the direction is changing, but generally it's based between the drain and source. Okay, so that means if you want, it makes sense that if you want describe the characteristics of your system, you use the IV characteristics defined by those two pins. So if you want to have the voltage input or output, that voltage is going to be the voltage that relates drain and source, or the voltage between drain and source, as we could call it. Okay, and the current is going to be the current that goes through the two terminal, which you're lucky because they are going to be in series. Okay, when they connect or they conduct a current, that means both current in a source and drain are going to be the same. So basically, if we consider the current of the drain, we are considering the current behavior of the whole main part of our transistor. Are we good? So we want to find the dynamic of the component. Dynamic is the IV characteristics. The main ports are drain and source. So when we want to define that, we use the voltage between drain and source as the voltage part, and the current of the drain, which is going to be the current of the source equal to current of the source, okay, as the current part. Okay? Now, the interesting behavior that these transistors have, because they have three semiconductor connected to each other, okay, is that when you don't apply any voltage to the gate, okay, is that each pair could be seen as a diode, right? If there is no voltage connected to the gate, then what happened? Let's say we have a voltage at drain, we have a voltage at the source, okay, but nothing at the gate. What the voltage, what these two pins see from the perspective of these two pins, they see one diode here, okay, which let's say it's NP diode, okay, so the cathode is here. For this diode, the cathode is here, okay, and then move on, and then they see another diode, but here the direction of the diode are in reverse. Is that clear? So if we what's happening? If we don't have any effect, or if we don't apply anything to the gate, so the gate is neutral, doesn't do anything for us. Okay, the signal that we have between the drain and source would see two diodes in phase, two diodes that are in the opposite direction of each other. So it doesn't matter what type of voltage you apply or what is the value of those voltage. Okay, one of those diodes are always going to be reverse biased. Is that clear? So if you don't apply any voltage to that gate, okay, that these two diodes, one of them are going to be reverse biased. That means no matter what's happened, we don't have any current passing through the semiconductors. Is that clear? Now, that aspect, we call it a state of work, we call it a cut off, because there is no current going through. So it's basically on that condition, when you don't have any voltage or any type of signal on your gate, there is no current. That means it's cut off. It cuts the current off. Is that clear? Now, so if we don't have any voltage between over the gate, if there's anything applied to the gate, no current, zero, everything. Okay. Now it doesn't matter how strong the voltage between the drain and sources. Now look at the semiconductors. We already kind of covered that in previous one. In previous discussion about the diode, we said we have a region, an isolation region, between the two semiconductor, that if we apply a voltage in a forward bias, we make that region thinner and thinner, so the charges would jump from one side to another. Remember that? Now, here, there are going to be the same type of concept, but with a little bit of change. Okay, it doesn't let me to, where is, okay, I don't have, oh, okay. With a little bit of change. When we have a voltage or any type of signal between our gate, between our drain and source, okay, this N type acts like a insulation. Now, you can see that the gate is not directly connected to that end. There is that white line, okay? There is an isolation between the pin gate and that end. Actually, that's the reason, the part that MO in MOSFET, it's metal oxide kind of like insulation between the gate and the semiconductor. Okay, so gate is not directly connected, so we cannot use what we used before in the diode to push the charges, okay, or affect that those two diode behavior between the on the other side of the transistor in the source and drain. But what we can do is that we have a gate near that channel. We can apply electrical field. We cannot apply or force charges. We can't inject any charges or drain any charges because it's isolated. But you can apply electrical field. Voltage doesn't need to have a current in order to create an electrical field or electrical pressure. Is that clear? So, if we apply an electrical field here, and this is a semiconductor material, what will happen? Any type of material. If you apply a voltage across any type of material in a molecule level, what would happen to those molecules? It gets polarized, right? So if we apply a certain amount of voltage to the gate, okay, we are creating an electrical field that would force those molecules, the semiconductor in the semiconductor, to be polarized. If it's polarized, it's not the insulation here. Now it can conduct. Are we good on that concept? Any question about that concept? Now, in order to define the voltage, because we already talked about that, the voltage is not like a scalar value, it's a vector value. So the voltage, when you want to define the voltage, you need 2 points. Voltage is between 2 points. So when we wanted to define or quantify the electrical field that we apply through the gate to that semiconductor, we quantify it as a voltage between gate and source. So we call the source, we keep the source as reference. Okay. Now the V on the IV characteristic was between voltage between drain and source, and now the control that we have, the force that we have to trigger the switch, we call it voltage between gate and source. Are we good? Now, when you apply the voltage between gate and source, this semiconductor, as we said, is start getting polarized or ionized, and then it start to create some channels near that gate that are now conductor rather than insulator or semiconductor. Okay, and as much as you increase the voltage between the gate and source, the width of that channel that you created would increase and increase all the way to a certain point, which we call the saturation point, which is the case that you have enough voltage between the gate and source that you already made the whole channel polarized. There is no more capacity for a kind of like ionization or polarization of the material. Good. So when we apply a positive voltage between gate and source, okay, then the transistor would have an internal channel to transfer the charges between the drain and source. So now you can get a certain amount of current. And based on the Ohm law, when the voltage between the drain and source increase, you expect the current to increase. Right? Now, so we apply, let's say this is the positive value of the gate source voltage. When we apply that, we have a channel, then we increase the voltage between drain and source, and Ohm law says that it should start increasing the current. Very good. Now, granted, Ohm law is treat the system as a linear impedance over resistance. We're talking about semiconductors which are not linear. So that's why you see like a knee type or exponential type curve instead of a line. Okay, but you can approximate that. That's not a big deal for us. So it starts increasing when the voltage increase, but you can see that after a certain amount of current, it gets flat. Why is that? The concept that we talked about. We have a channel. If we have a specific width of the channel, that means we have a specific capacity of conducting current. When we occupy the whole channel, it doesn't matter how much VDS you force to the transistor, it doesn't have the capacity to conduct more. So it gets saturated. Any questions so far about the definition and the concept that we talked about? No? Okay. Now, all that said, we can define and see the IV characteristics of a MOSFET based on the curves between the drain current and the voltage between drain and source for a specific amount of voltage between gate and source. So we have three variables here. Okay? The IV characteristics is between the drain current and the VDS, but the curve also changes. It has a dependency on the value of the voltage between gate and source. Is that statement clear? Any question about that? So based on that, we can say, okay, if I have voltage between gate and source as 0, my semiconductor do not conduct the channel. Okay, because I have two opposite way diodes. So I expect to have 0 current regardless of the voltage of the drain and source. Are we good? So we define that as a cutoff region. So if we have 0 voltage at gain and between the gain and source, we are in a cutoff region. No current would be transferred between drain and source. Now, if we apply a voltage between the gate and source, now we are starting to polarize the channel, making it conductor. Okay, now we are allowing the current to pass. Still, I wanted to again remind you of a concept that we learned about the diode. Remember when we wanted to turn the diode on, basically meaning we enter the forward bias. Okay, we had a threshold. It was not like any value of positive voltage in a forward bias would give us the current. We need to exceed a certain amount so we are actually able to force the charges jump from one semiconductor to another. Same concept goes here. It's not like any value of the voltage between gate and source give you the enough electrical field or enough pressure to polarize that channel so you can have your current. You can look at it like that. Let's say this is my channel. Okay, I want to transfer the current through that, and I have a gate. Voltage is between gate and source. Okay, this is gate, this is source. When I apply the voltage, it starts to ionize here. Okay, or polarize here. I have to apply a certain amount of voltage, so at least I have a tiny bit of pass on the drain side. Because as much as I apply voltage on the source side, I would have a bit, but this is the voltage between gate and source. So on the drain side, I don't have that amount of pressure. Does that make sense? So I need at least a certain amount, a threshold, so I make sure that I have a channel through the semiconductor. So that means I have for VGS, I have a certain amount of threshold that I have to. So I could exit the cutoff region. When I exit the cutoff region or meet that threshold, now I have a channel to conduct the charges. Okay. Now I can have the current based on the VDS. So I have a current. The part that the current would be dependent on the voltage between drain and source, meaning we are not saturating the channel yet, we call it a triode mode. On that mode, current of drain is still dependent on the value of the voltage between drain and source because we are not saturated. Channel is not saturated, so as much as you increase the voltage, you are going to increase the current. But when you hit the saturation part, then it doesn't matter what is the voltage of the drain and source is, current would not pass over that saturation bar. Then you are, it's is on the name, you enter the saturation region. Saturation. So when we talk about the IV characteristic transistor, we have three modes. Cutoff mode, which is we don't have a voltage between the gate and source, or the voltage is less than a threshold, less than a value that we need to create a channel, or we have the channel but it's not saturated. And the third one is that we have enough charges passing through the channel as saturated, and now we are in saturation. Very good. Now, it goes without saying, and you can see that in the graph, that when you increase the VGS, okay, the amount of current that you can get would increase. You can see that. Like now, like the second VGS that I defined is more than the first one. That means I have a wider channel. So I can provide more current. Right? I can transfer more current between drain and source. So that means, yes, my curve is gonna be is gonna have a higher saturation current. And as much as you increase the VGS, it would go higher and higher. Any questions so far? Remember this, I don't want you to like kind of like understand the whole theory behind this formula, but when you are in saturation mode, that Kn is defined in a datasheet, it's given in a datasheet. So basically, if you have a datasheet and you know how much voltage you apply between gate and source, you can easily calculate how much current you're gonna have. The threshold is constant based on the type of MOSFET that you have, but it's also into datasheet. So that formula is very handy when you want to fastly calculate what's happening in your circuit in saturation mode. because Kn and Vth is already given in the datasheet, and you just need to have your gate and source voltage to find out how much current you can expect out of that MOSFET. Any question about that? Is that clear? Now, one thing I want you to pay attention to, and it's mostly a practical kind of like this. We normally don't use MOSFET in a triode. Okay, we want to use it in a saturation because we normally use MOSFET as the switches. We want on and off situation. Okay, in triode mode, the value, the curve is dependent on the VDS. If we want 0, 1 kind of situation, okay, switch on and off, we don't want the dependency of the condition of the circuit. We want to turn on and off without considering what's happening in the power system or a general signal in the circuit. Is that clear? So, because we want to use that as a switch, we normally tune the MOSFET or use the MOSFET in a saturation mode. So either it's conducting that I saturation or it is not conducting at all. Is that clear? Now, as we said, we have two types of, oh, sorry, this is BJT. We already talked about the MOSFET and the two type of MOSFET, N channel and B channel. The second transistor that we want to talk about is the BJT. There are also connection of 3 back-to-back semiconductor. So either we have NPN or we have PNP. Okay? Now, the difference between the MOSFET and BJT is that the middle pin, which still here is also a control pin, okay, is directly connected to the semiconductor in the middle of the whole transistor. Before in MOSFET, it was isolated. Now, it is connected. Okay? You can see the symbol of the BJT. It has three pins. Here, we call the pins as collector, emitter, and base. Collector and emitter is similar to the drain and source that we talked about. These are the main pins, the general signal pins, and the base is the control port. We control the IV characteristics of the BJT, or choosing in what condition or in what region or state the BJT is working by setting the condition in the base. As we said, we have two types of BJT. One is NPN, which means the middle one, the base is connected to the P type, okay, or NPN or PNP, which is the base is connected to the N type. NPN here, in NPN, the current goes from collector to emitter. Please pay attention to the directions. On PNP, current goes from emitter to collector. Again, think about that. Is the same concept that we had for the MOSFET and the diode. You know how the reverse forward bias works. You can think about that and understand why the current changes the direction. Okay? Now, when you look at your BJT, okay, you will see in the lab, you will see a component with a 3 pin. That component has a flat face and a curved face. If you look at the flat face, like the flat face is facing you, okay? In the NPN, remember, this is different, see? Well, not different actually. In the NPN, the far left one is collector, The far right one is emitter, and the middle one is base. Now, let me, I missed that to tell you here. Let me also give you that same concept for the BJT, for the MOSFET. In MOSFET, again, you have a flat face and a curved face. When you're facing the flat face, the far left is drain, then it goes to the gate, and then the right one is the source. Okay, so that's how you can find which pin is which when you want to connect it to the circuit. Are you good so far? Now, same as before, same as MOSFET, we also need to have an IV characteristic for the BJT, okay, in order to be able to analyze it in a circuit, like every other component. We already talked about that. Okay, now there is a very fundamental difference between the MOSFET and BJT when you talk about the IV characteristics, and more specifically about the control signal between the two. Before in MOSFET, we said gate is isolated, so we apply a voltage to create electrical field. In BJT, the control pin is directly connected to the semiconductor. Okay, that means when you have a voltage, you are going to have a current. In MOSFET, that wasn't the case because it was isolated. Here, you will have a current if you apply any type of voltage. That concept is one of the biggest difference between the two when it comes to controlling those transistors, which says in MOSFET, your control signal is voltage. In BJT, your control signal is current. So if you want to control a BJT, switch it on and off, or use it as an amplifier, we're going to talk about that in a minute, you have to tune the circuit or control the circuit using an injected current. Okay? Granted, you are going to use a voltage to create that current, but you need to pay attention that the actual controlling force that you have, the leverage you have, is the current that you're injecting into BJT. In MOSFET, it was just the voltage. Is that clear? Now, same concept between the like we talked about the MOSFET goes from the BJT. If you don't apply any current into the base, the collector and emitter will see two diodes back to back, or like in the opposite way. Okay, so no current. Doesn't matter how much voltage you have between the collector and emitter, you would not conduct any current between them. Okay, so same definition, we call it cutoff region. Now, when you start applying the current into the base, okay, you are actively pushing charges to that semiconductor, which basically means you're polarizing or ionizing it, whatever you want to call it. Okay, that means you are creating a path for the charges that go between to transfer between the collector and emitter. So if you have a certain amount of current in your base, then your BJT will be able to conduct current between the collector and emitter. Before saturating the channel that you created, like the MOSFET, you are going to see a somehow linear behavior between the voltage of the collector and emitter and the current that passes through those two pins, which are in series, so they share same current. Not exactly true, but approximately same current. Okay. And when you are saturating that channel, again, like MOSFET, then you're capping your current. It doesn't matter what is the voltage between the collector and sources, your current is going to be the same amount of current. Is that clear? Are we good on that? Now, here, honestly, I don't know why they did that, but the difference, that the naming of the region are different. The part that we have linear behavior or semi-linear behavior when the current changes based on the voltage between the collector and emitter. Now we call it saturation region here in BJT. And the part that current gets saturated, we call it active region. Okay? So just try to note those so then don't get confused. It's different. The naming are different between the MOSFET and BJT. Okay? So now, one very interesting behavior of the BJT is that the amount of current that you can actively transfer from between the collector and emitter, either way, based on the NP and PNP kind of like a situation, is triggered by the current in the base. Okay, so for example, if you have IB equal to like A naught, you would get in active region, you would get an collector current of B naught. Okay, if you increase that current, the base current, you increase the collector current. That gives this BJT a very interesting characteristics, which we can use it or define it as an amplification. Okay, and the fun part and the interesting part is that for each specific BJT model, that amplification ratio, when you increase the IB, the ratio that it would create the increase in IC is constant. So it doesn't matter what is the current of the basis, that coefficient would apply to that current of the base and gives you the current of the source. And as you can see, we are talking about the active region, okay? So we don't like this part. We are talking about the active region. And as you can see, this current of the collector doesn't have any dependency over the voltage between the collector and emitter. So this behavior basically gives us the ability to say screw Ohm's law. Now Ohm's law doesn't affect your current. It doesn't matter what is the voltage or KVL of your system when you have a BJT. The current passing through the collector is defined based on the current of the base. Doesn't matter what is the KVL of your systems. Is that clear? So when you want to analyze it, don't run KVL. Find out what is the base current is. The current through the collector and emitter is going to be the coefficients times that current of the base. Now that coefficients, theoretically we call it beta, the Greek letter beta. Okay, as you can see here. So meaning the collector current is beta times base current. In the data sheet of those BJT, this also referred as HFE. Okay, so this is lowercase e, sorry. HFE is the same as beta. So if you find something HFE equal to something, it's the same concept as beta. So that's the coefficients that defines the behavior of your BJT in the active region. Any question? That little behavior gives us the ability to use that BJT as an amplifier. So you inject the signal, a very weak signal, to the base, and normally BJTs has like over like 100 to 200 beta. So you are gonna get a very amplified version of your weak signal at your collector. Make sense? Now, in eLab, we are going to talk about these amplification and we are going to actually build those amplifier. So just for now, just remember the concept. Now, when I said that current of the collector and emitter are, we can approximately say they are equal, okay? I meant that actually they are not. And why is that? Because unlike the MOSFET, that the gate was isolated and there was no participation of the current from the gate, because the base in a BJT is directly connected to the semiconductor, then whatever charges that you toss in from the base into the whole situation, okay, like a KCL scenario, would affect the amount of current that passed through the semiconductor. What I mean? These are all connected to each other, directly connected to each other. So if you run a KCL here, you have a current here, you have a current here. It makes sense that the current exiting from that emitter should be the summation of the two. In MOSFET, gate would not participate in the current because it was isolated. Here we are directly connected, so we're participating in the current. So if you wanted to be precise, the emitter current is actually equal to the summation of the base current and collector current. But why we say approximately they are equal, emitter and collector current? Because we said this IC is beta times base current. That means this one is actually collector current over beta. Very good. So basically, IE is 1 plus beta IC. Right? No, 1 plus 1 over beta. Sorry. IC. Correct? But beta, we said, beta is normally over 100 or 200. So it's a very tiny number. So we can neglect that. Approximately say, emitter and collector have the same current. Are we good? Now, let's talk about the exercises that we have. In this lab assignment, you have 4 exercises. Exercise 1 is to find the IV characteristics of the MOSFET, more specifically BS170, which is an NMOS. Okay? Now, what you want to do is to apply a certain amount of voltage between gate and source. This was how we trigger the MOSFET, okay? And find out how much current would pass through the circuit, or more specifically, what is the current of the drains. Are we clear? Now, you want to measure the current. You already know you have a digital multimeter. If you want to measure a current, you need to connect that in series with your component. That means either part of the circuit, this multimeter should be here. In series, remember, in series with your MOSFET. And then here, either you can use the signal generator or one of the channels of your DC source, because you have like 3 channels in your DC source. And I believe this one is 5 volt. So you don't even need to like use one of these 2 variable channels. You already have a fixed 5 volt channel 3, okay, in your DC sources. Either way, You can use one of the variable channel for your VGS and apply the voltage between gate and source, and half a volt with a half a volt step, increase the voltage, find out what's going to happen to the drain current. Up to the certain point, which we said is a threshold voltage, you should see a very tiny value for the current, which is the leakage current. We already know that. We say there is no current, but reality is not like here. Okay, so there is going to be a leakage current, but it should be very, very small. Okay, now you apply the voltage, you increase it little by little, and read the current. Now there is a point in your increasing the voltage of when you increase the VGS that suddenly current start to jump. Okay, suddenly it start to conduct a kind of like a notably massive, relative massive amount of current compared to points before that. Okay, that level is the threshold. Are we good? Now, this transconductance parameter, transconductance parameter is that K that we saw on that formula. You remember that? The formula that says ID is Kn VGS minus V threshold square. It is in the lab assignment. I already mentioned that in lab assignment. You don't need to memorize that. By having the measurement, you already have the V threshold. You find it already. That's the point that you have a jump in the current. One of the points, you're going to choose one of the points that has a notably measurable ID, meaning after the threshold, and use the current and the VGS for that point to calculate the Kn. So for example, here, you have the VGS, you have the current, okay? You know the threshold is somewhere between these values, okay? And then it's just like a division, a very simple mathematical derivation. You find the Kn. Are we good? Now, for the next part, for the exercise 2, we want to see in a more tangible way how the MOSFET works as a switch. Okay, so we are gonna put the LED in series with that MOSFET and connect. Why is that connected? Connect the gate of our MOSFET to the point of voltage division between a constant resistor and a variable resistor or potential. So you have a constant resistor and a potentiometer in series, okay, which create a voltage division, and you connect the middle point between these two to the gate. Now, if you change the potentiometer, you're changing the voltage division. That means you're changing the voltage of the gate and source. That means you're changing the mode of your transistor. Now, there is going to be a certain, you already, I think, by that part, you already know, there is going to be a certain value of the voltage that will turn on your transistor. That means your LED would light up. And before that, you would, for the voltage lower than that, the LED is off. So for both situation, LED on, LED off, you need to measure the voltage of the gate, okay, which is here. And when I say gate, it should be gate and ground. Okay, so it's basically gate and source. Okay, and then you have to measure the current that conducts here, current of the drain. Okay, and the rest is very easy. Voltage across the 1.2 voltage here, voltage of LED, and the voltage across MOSFET, which is the voltage between the drain and source. and I think you already know how to use the voltmeter. Yeah, well, oh, yeah. It is valuable. You should have a 1K potentiometer in your packet. Yeah. So that would help. That would give you the enough kind of like variability to have that. The power dissipation of the MOSFET is optional, but since you already calculating honestly, if you're already calculating the voltage between the drain and source, and you already measured the voltage drain and source and measured the current of the drain, you have the power. It's just two push of a button on the calculator. You know what I'm saying? So don't get kind of like, I don't want to say lazy, but don't forget that do that. It's optional, but do that. Any question about this assignment? No? The next one is for BJT. Now look at the signal where you see a resistor between the input or the control signal and the base. That's why I said the BJT works with the current signal. That resistor translates the voltage into the current. Okay, so by that resistor, now you have defining a current injecting to the base. This is a KVL here. Okay, now you set the voltage of base and emitter. This is one constant voltage. You can use 5. I think it's 5 volt based on the assignment. You can use another channel of the DC source for base emitter voltage here. Okay, and start increasing the voltage. You can also use the signal generator. Doesn't matter at this level of voltage, both works. And then you have to measure the current of the base here. So your amp meter is in series with that resistor. Are we good? You are measuring the current injected into the base. Yes. Yeah, I'm sorry. I was past a little bit. I understand that, but just one exercise. Okay. Any question? No. Last one is also not too problematic. It's basically wanted to show you the amplification characteristic of the BJT. You set your input, which is the base emitter voltage, and you change it with a DC source, and you know how to change the polarity already. You've done that before. And you have to you have to measure both the current of the collector here, the current passing through this resistor, and the voltage between the collector and emitter. Now, my suggestion is to use the digital multimeter as an amp meter, okay, in series with that resistor, and one of the channels of your oscilloscope for measuring the voltage between the collector and emitter. That makes your life easier instead of like doing one measurement and then start another one from the sky. You know what I'm saying? So because you have one voltage, one DMM, use the DMM as ammeter and use the oscilloscope as a voltmeter. Then for one test you have everything. Are we good? Any question? I already posted a video of myself doing that. You have access to that in Canvas. Review that. If you have any question, let me know. Otherwise, thank you very much, and we are done for today.